Assalamu alaikum students. This is lecture 10 for DSP triple E 324, and in this lecture we will be looking at the topics of frequency response, magnitude squared function of frequency response. Then we will be looking at all pass systems, and then we will be looking at minimum phase system. So, as you recall in our earlier lectures, we have been looking at how the Z transform and the Fourier transform can be used to analyze LTI systems, linear time invariant systems. So now let us see and recall that a rational system, LTI system, can be described by the system function h of z, as we know, and h of z is of the form of a polynomial in z inverse over a polynomial in z inverse, right, of degrees m and n. So if we have a system function h of z, we can from our system function, if we have an h of z, we can obtain the frequency response h of e j omega, and we do that, we just replace in h of z, for z we replace e j omega. So h of z evaluated on the unit circle gives us the frequency response h of e j omega. So given if we have an expression, if we have the system function for an LTI system, we can just obtain the frequency response. We want to know the frequency response of the system, then all we have to do is replace, instead of z, we replace e j omega, right? So over here we replace it for z e j omega, and then we have this polynomial in e to the minus j omega of degree m divided by a polynomial in e minus j omega of degree capital M. So from system function we can find the frequency response h e j omega, and that's why it's so convenient to have these different representations of the LTI system in the Fourier domain and in the Z domain. So we can get an expression for the frequency response. We can express h e j omega in terms of the poles and zeros of h of z, the system function. That is, if we factorize h of z into factors, the poles and zero factors, then if we replace by e j omega, we get h e j omega in terms of these poles and zero factors. So this is our frequency response expressed in terms of pole and zero factors. And if we want to find an expression for magnitude frequency response, then the magnitude of h e j omega, since h e j omega is a product of all these factors, so then the magnitude of h e j omega, because it's a complex number, so the magnitude of a product, as we know, is the product of the magnitudes, and so magnitude h e j omega is a product of the magnitude of all these terms, the product of all the zero factors. So these are the zero factors in the numerator, and divided by the product of all the pole factors. So that's how we can think of the frequency response. So just instead of just having frequency response as a polynomial in e j omega, we can have it in this factorized form, and as a product of the magnitude of zero factors over the product of magnitude of the pole factors, and it becomes more convenient actually to have it in this form. Sometimes it's more convenient to have a expression for the magnitude squared function, and right, in some cases we will require magnitude squared functions, as in our later discussions when we design filters, then this we will come across this magnitude squared function there also. So to get an expression for magnitude squared uh, function, what we can do is that we know that for a complex number, if we multiply any complex number a with its conjugate a star, then what we get is the magnitude of the number, right? Complex number into its conjugate gives us actually the square of the magnitude. So that's why we can use this method to find the magnitude squared function or expression for HEJ omega squared. So when we right, so in the HEJ omega we multiply HEJ omega and we then take a conjugate of all the terms. So HEJ omega was the product of all these zero factors and divided by the pole factors, and this b0 over a0 term, this actually we right when we have hc in the form of a polynomial b0 plus b1 z inverse and so on, then we actually take this term out. So this term actually comes from there. So right, so over here we have our HEG omega, and this then we conjugate each of the zero factors, we get this factor, and each of the pole factors are also conjugated, and this is HEG omega into H conjugate EJ omega, and this is the expression for, and this way we can get an expression for the magnitude squared function of the frequency response. We had earlier expressed the magnitude of the frequency response as a product of the pole zero factors divided by the product of the pole factors. It could be more convenient to express this product of HEJ omega. Instead of keeping it as in the form of a product, we can express it as a sum by taking logarithm of both sides of the left hand side and the right hand side. So on the left hand side we have 20 log to the base 10 of HEJ omega, and the product terms become a sum. So the product of the zero factors become this sum, summation from I is equal to 1 to m, and the n pole factors, when we take the logarithm we get this sum, and now this expression 20 log to the base 10 HEJ omega is also known as the log magnitude, and we will be evaluating these quantities when we analyze the different LTI systems and we take their examples. We will be computing these quantities. So 20 log HEJ omega is also called gain in decibels or the log magnitude. So these terms were also discussed in previous lecture by Dr. Fassi. And let's take an example. Suppose the system has this magnitude response, HEJ omega is equal to 0.001. So when we compute that and take the logarithm, that is log of 0.001 is minus 3, and minus 3 into 20 we get minus 60 dB gain, and because the gain is negative we also call it attenuation. So we can say the system has a minus 60 dB gain or a 60 dB attenuation. And another example, if the magnitude response is 1, this becomes 0 dB gain, log of 1 is 0, and for magnitude HEJ omega 0.5, the result is minus 66 dB gain or 6 decibels attenuation. So for a LTI system or a filter, it could have these different magnitude responses, and attenuation means that the LTI system or filter is applying attenuation, or this is the response that it gives in the stop band, right, for a LTI system. So these are various terms, and this is the log magnitude, and then we can also see an expression for the phase of the system. The phase response is computed uh, as the contribution from the zero factors as well as from the pole factors. So the phase is the sum of the phase of each of the zero factors minus the sum of the phase of all the pole factors. So we recall HEJ omega was a product of the pole factors divided, zero factors divided by the pole factors. And the group delay, as we recall, a group delay is obtained by taking the derivative of the phase function. So group delay, that is the amount that a signal is delayed when it passes through an LTI system, is obtained by taking this derivative of phase function. So we have a term here d by d omega of all the phase of all the zero factors and all the pole factors. So this is the group delay um, expression, the expression for computing the group delay. So these are some quantities that we defined, that for an LTI system we can find the frequency response from h of z from the system function by evaluating it Hej omega at z is equal to Ej omega. Then we can get magnitude, an expression for magnitude frequency response. We can get an expression for the magnitude squared function, for the phase, and for the group delay. And as we do further examples, we will see the use of these quantities.